bioscientist here at the Franklin Institute. Although I think my more appropriate role for today's conversation is just professional science nerd, because we are going to be talking all about engineering. And the Franklin Institute actually has a long history of nerding out about engineering, because going all the way back to 1922, we gave a Franklin Institute award to the chief engineer who designed the Benjamin Franklin Bridge. Interesting anniversary coming up for that soon as well. But we're talking about much more recent events on our conversation today. Many of you have probably followed the ongoing construction and reconstruction of the bridge that collapsed on I-95 just north of the city. And to everyone's really surprise and pride, the engineers who worked on that project were able to get a temporary roadway up and running in just 12 days, which is really cool.
Yeah.
And so I'm lucky to be joined today by Mike Mahalik, who is Vice President of Transportation Services at McCormick Taylor, to help us understand how it all happened, and what the future of that project is, and what this kind of project tells us a little bit about the state of engineering of our infrastructure today. So Mike, thank you so much for joining us.
You're quite welcome. It's really an honor to be here. Thank you for having me, and I'm excited to talk about it and engage in not only the science and engineering of what happened, but how we might be able to, provide this as an educational outreach for everyone to understand about exactly where the field of transportation is going and what that means for everyone.
No, we're so honored to have your expertise. And before we dive into this project, tell us a little bit about yourself, because you're Philly born and bred, but you've had experience on both coasts.
I certainly have. So I'm proud to say that I'm born and raised in Philadelphia. I grew up in the Olney section, and I am a graduate at Drexel University, Central High School before that. So
Lots of local connections.
Yeah, lots of local connections. After I graduated Drexel, I went to California, and I worked for the California Department of Transportation. That's the equivalent of PennDOT here. And I was fortunate enough to get a lot of education in engineering there and go through a rotational program. And part of my work there was right around the Loma Prieta earthquake that happened, and what the state at that time was doing to help seismically retrofit some of their largest structures and interchanges there. And I worked there for about 5+ years, and I moved back to Pennsylvania and joined McCormick Taylor. And I've been there working in their transportation department, and now running the engineering services for McCormick Taylor for the last almost 28 years. And so it's been a pleasure to be back. And thanks.
Yes, that's great. And certainly, we may not necessarily have to deal with as many earthquakes here on the East Coast, but plenty of challenges to think about from an engineering point of view. So let's start by talking about, the damage to the original bridge. We all heard the story about, the tanker exploding underneath that short span of the highway. What was the original bridge made from, and what was the damage that was caused by the explosion?
Well, it was a steel beam bridge. And obviously on top of that you had a riding surface. There was also concrete combined with the steel, and then there was a riding surface on top of that. So in this unfortunate event, we had the tractor trailer that exploded underneath the bridge, and that tractor trailer had about 8,500 or so gallons of highly flammable petroleum within there, and the temperatures that that causes really caused the steel to actually start to melt from the underside of the bridge. And during that process, it loses its strength, it begins to bend. And you have to remember, at that same time, with all of that fire and flame going on, there were cars still driving over it. So it was still getting a load. And as it was taking that load, but in the weakened steel condition, it began to bow. It would create a U shape from the constant pressure coming down from all of those cars. And I think even some of us saw some of the news reports where they had northbound drivers describing they felt like they were going off a curb, and there would be a depression. Well, that was the steel and concrete bending before it ultimately gave way. Fortunately, the smoke and other conditions prevented traffic from continuing. So we avoided what was even a larger tragedy by having the traffic stopped. But then ultimately, that heat and the stress on the steel, which was causing to elongate and flex and bend, ultimately collapsed onto the roadway below.
And you had mentioned when we talked earlier, a really, I think, a helpful analogy in thinking about what was happening to those steel beams, thinking about what happens with a coat hanger in a couple of different ways.
That's
Can
true.
you describe that
Yeah.
analogy?
So what happens is, as these beams can experience stress, and they can experience stress in a variety of ways. One of it would be, say, repetitive loading, like heavy traffic constantly going over the beams, which would, if you think of a long coat hanger, would be the same thing. So a constant loading could cause something that, as it begins to bend, if you think about a coat hanger bending back and forth, ultimately you're going to see weak points at the bend of that coat hanger. We've done this all ourselves, I'm sure, and then the coat hanger will snap. Well, another way that can happen is if you have intense heat. The intense heat will weaken that hanger. So as opposed to a bending motion like this, the heat will cause it to thin out, the particles to break away from one another within the steel. The carbon atoms will unbind, so to speak, from one another. They'll elongate. It won't be able to take the load anymore, and it'll bend to a snap, as opposed to a back and forth motion. It's another way that the beam would fail due to the high heat and continual loading. And essentially, that's what happened here in this case.
Right, and so that's kind of why we see the part of the roadway that was directly above the heat really just collapsed and gave way,
Exactly.
even more so than the part that wasn't quite as directly over the heat source.
Exactly. That's why you would see that. And then, outside of that area where the roadway was on a fill material and you didn't have the beams, you saw that was not compromised. Really was directly over just the ramp area where we had the exposed beams.
Right. And so, both sides obviously were not safe to drive on. So the first step was to demolish any existing structures and clear that out. But let's jump into the temporary fix. What was the overall design strategy for that?
Yeah. Well, before I hop into there, I just want to say, they had the demo, and we talk about this as an engineering problem, but this was really a collaboration by all sorts of people, even before it got to an engineering solution, because, the rapid response of the incident management teams to get people off of the roadway and diverted onto the side roads, and certainly the EMTs, fire, because really at that, it really was an emergency rescue and hazmat situation is what occurred
Sure.
first, right? Because there was, concern about that with the petroleum. So, I can't say enough about the great work of the non-engineering aspects of this associated with how PennDOT, the city, the Department of Streets, the incident management teams, EMT responses, and even the police and fire, who played an integral role in really collaborating in a way that was unprecedented to get this under control. So within a day, you could get to a demo operation. It truly was
That's such an
amazing.
important point. Yeah,
Yeah,
because for all of the science and engineering that we can design hypothetically on a computer simulations, right? When it hits the real world, there's so many more factors to consider.
absolutely. And fortunately, unfortunately, there was an incident a few years ago with a tire fire. So there were lessons learned, and hats off to all the parties involved who learned from those lessons and were able to employ some of the things that they learned from years ago with the tire fire just south of this location to really come through this in a way to get us in a spot to what you're describing of getting to a demo and a temporary fix so quickly. So that was instrumental. Certainly worth noting for all of those people who played a crucial role in that.
Well, so then help us understand how some of those past incidents and lessons learned led us to the idea for this temporary fix.
Well, some of the things that happen, like I mentioned, incident management plan, which means when you have an incident, right, which happened here, whether it's either it could be a fender bender, it could be a large scale event like this, how do you manage that? And where do you divert traffic to? And what does that look like? And can the local grid network handle that? And then how do we communicate that to even people such as SEPTA and other places who might be able to provide emergency relief, add additional shuttle services, get it to the news outlet to provide diversions, and put some variable message signs up. All of those things we learned about how do you quickly respond to things. Um, there was a lot of other fortunate things that were happening at this time. We never like to drive through construction zones, and it always plagues the motorist, particularly on I-95. But in this instance, having knowledgeable people on site, having equipment readily available that they could quickly mobilize to this location, and having engineers and contractors already employed by the state and the city that could quickly respond allowed them to be very nimble and flexible and able to do all of that. So those kinds of lessons learned about, well, where do we put the traffic? How do we create a rescue and recovery operation so that we can get things moving again, all came into play. And they did a spectacular job at it.
Yeah, one of the silver linings of having to drive through construction on that stretch of 95 for so many years.
For instance, yeah, we never thought we would be happy to have some construction ongoing, but in this case, it really did play into everything. Yeah. The other,
so let's talk about the temporary fix. So, the decision was made to, kind of fill in the space underneath the roadway and build a temporary roadway on top. Can you talk a little bit about the engineering that went into deciding that was the most straightforward or, most feasible first course of action?
Well, sure. There was several things to consider there. Well, obviously the ramp already had to be closed. So that played into a solution already. The ramp is already closed. So if you could create a situation that took advantage of that. And so by placing fill there, you take advantage of that. You also have the ability that there is an upstream and downstream exits and entrance points to I-95. So you could get the main traffic back on with still having that ramp closed, because you could access Cotman Ave and Linden Ave and Academy Road either north or south, even with this closed. So from that standpoint, just from a practical matter, it made sense. A few other things come into play, which is this material that we're talking about. We can talk a little bit more in depth about it. Is readily available. The plant that was producing this, Aero Aggregates, is just south of the airport in Eddystone. And so they had it readily available, and it was very close, and it's very lightweight. So you're really only limited by how much you can get there and truck there as fast as you can. So because it's lightweight, and you can get lots of this material there quickly. And it is proven. It's a good material that's actually even on several other places along I-95, it's already been used. So it's been proven. We've used this material, behind some retaining walls, to fill some ramps, to widen roadways, behind retaining walls. So there's a history there. And so then why I say that's important is because there's a confidence in it, but also people know how to work with it. There's a familiarity with the product and what you need to do with it. So and you certainly want a fast solution, and this lends well to the fast solution, even just from the material standpoint. Another important part of it is the placement of it. So once you get it there, you have all this material, right? 10,000 plus cubic yards of all this material. It gets placed very quickly. So you can put this material down and say, 2-foot lifts, 2 feet at a time, you can put it down. But with traditional dirt or soil or backfill material, you would have to put it down. You likely have to water it and then roll it with a machine and then keep testing it, put another, let it dry, make sure there's no pumping. And that's time consuming. With this material, the ease of construction is much quicker. You can almost, and in some cases, the same material that's dropping it off or what might be on site with a small dozer, you just simply run a few passes over it and you don't have to keep watering it. Actually, it's a non-porous material. It goes in very quickly, so you can get these lifts in.
I think that helps a lot of us who were probably dropping in on the live stream camera on the construction site every so often. It really helps you understand how we were seeing progress that quickly.
Yeah, and you know what? You bring up a very good point with that. A lot of the, I don't want to call it skepticism, but the nervousness that the public or someone else might see about this is the not knowing. So the idea to have it live streamed and for people to be part of it and to see a solution and to feel the groundswell of all of the collaboration going on, to have a confidence about what was going on, that really helped. I know when you're in the business with Franklin Institute, that's one of your missions, to educate people about things. I
Yeah.
felt like this way the whole Delaware Valley was educated about what was going on, and they became a part of it, and it made more sense to them because of that.
Yeah, we had a question come in from the audience, like why were people so invested in that construction live cam? And I think absolutely, it's that little window into the process that I think fascinates everybody. And one of
Yeah.
the cool things about this particular problem is that I think everybody understands what the problem was, where the solution needed to go, and how it impacted our lives. And so we were all really interested in understanding how we get from point A to point B.
Absolutely. And we feel it throughout the Delaware Valley and the 5 county area here, right? That, it caused some changing of our schedule, so to speak. But we have to understand, through the Mid-Atlantic region, when we have goods and services coming in from the Baltimore Harbor, even the Philadelphia Naval Yard, all the way to places in New York and New York Harbor, it's a big commercial corridor. It's a way that
Yeah.
goods and services go up and down the East Coast for a variety of reasons, including maybe some of the local channels within the Delaware River aren't as deep and they can't get this product, so it gets offloaded. And you hear this highway has 160,000 vehicles a day on it, which is a lot of cars, and 8% of that number is trucks. So that's goods and services that we didn't want to interrupt along that north-south corridor. So it was important for the entire region, really.
So I want to come back and talk a little bit about that aggregate glass
Sure.
material, because I think it is fascinating. I'll put in a little shout out to a Franklin Institute connection here. Many of you who have been to the Franklin Institute know that one of our iconic exhibits is the Baldwin 60,000 locomotive. And in fact, after the Baldwin locomotive works, discontinued production, that facility became the site at which Aero Aggregates now produces these foam glass aggregate materials. So it's interesting to see
Yeah.
how industries kind of roll from one technology to another over time, not just conceptually but literally physical location as well.
Yeah.
So tell us a little bit about
Sure.
you talked a little bit about these foam glass aggregates. We heard a lot about how it's made from recycled glass. What is
Yeah.
that process?
Yeah, it's pretty interesting, right? Because the engineering now breaches over into technology and then connects to sustainability, right? Because this is made from recycled material. So a lot of the glass that might be headed towards the landfill or other waste disposal areas can be diverted. And that's what happens here. So we're talking about your regular glass drinking bottles, even your beer bottles, window panes, mason jars. It doesn't matter if it's clear or brown glass. It's all gets diverted and it gets to the plant. And essentially what they do is they mill it. They mill it into very, very fine particles, almost depending on which type of aggregate they're making, even a powder type form of this. And they take that granular material, this powder, and they inject it with a foam injection, which sort of makes it here's a good engineering term for you, the puffiness of the aggregate, and it makes a paste. And if you can imagine what a pancake might look like, it's a long conveyor belt with this material on it, and it gets heated very quickly and very high, probably somewhere around 1100 degrees plus or minus Fahrenheit. They'll quickly heat this powder foam mixture too, and they put it through on a conveyor belt, but then it's rapidly cooled. When it comes out and hits air temperature, there's not a graduated cooling process. It's instantly cooled, and when it comes out, it's probably around 100 degrees. And that
Wow.
instant process of that will cause cracking and fractures within the actual what this pancake material I described. But now it's hardened. It's hardened rock, and it breaks like that. It breaks very angularly. If you've seen it, it's not round. It doesn't look spherical. But it has angles, and that's one of the attributes of this. These angles at which the material splits, they call it the friction angle. So the internal friction angle is kind of high. It's around 45 degrees, which means that it has good sustained bearing of capacity for it. it's if something's loaded on it, it just won't shear off. It has an ability to withstand a load, and it's super lightweight. So that's the nature of this product. And the one being used here is non-porous, so it won't absorb water. So you might say to yourself, yeah, but when I look at it, it looks like it has holes in it, which it kind of does. There's air pockets, but those filaments or capillaries aren't continuous, so water isn't going all the way through. And that's how you get this material. And it's super lightweight. It's super durable. It doesn't corrode. It's a good insulator. It's frost resistant. And it might be a little bit more expensive than regular, say, dirt or fill material, but it has all these other advantages too, and it's
Right.
readily available. So
And one of the advantages of it being lightweight is that it doesn't put as much pressure to
Absolutely.
pipes or other things underground as well, right?
Absolutely. So you make an excellent point again, because that was one of the concerns here. On this ramp here, there are utilities there, and I believe there's a stormwater and sewer pipe there that you can't put that much dirt fill on top of it, because it would crush it. It would compromise, the utilities that are underneath. So this material can be placed, and because it's lightweight, you're able to place a lot of it very high without damaging something that might be under it, like a utility, or you could put it above a tunnel. You won't have to worry about a tunnel collapsing, or just say the existing dirt that's out there right now isn't very good, or doesn't have good sustaining like capability to hold stuff up. Well, you would use this on top of that as well, because it doesn't need to carry the overburden of the fill material above it because of the lightweight nature of it.
Right. So obviously, we talked about this being a temporary solution because it is, blocking off the ramp underneath. And so what's the long-term, fix for this section of the road?
Yeah, I know a lot of people are wondering about that. And I know people wonder too, well, why not just leave the temporary place there if that's working? But the long-term fix is to essentially put two bridges back, almost mimicking what was there before. And I don't know for certain, but I would surmise that they'll just use the same design or a very similar design of what was there before. I believe the bridges that were destroyed here were about 10 years old, which is not old for a bridge at all. So they have existing plans that they can look off of. They have existing designs that they know can work. They're using similar type structures all up and down this corridor. So that's another advantage. They have an experience with how to build it. They have materials, and they have designs that they know can work. So they'll likely, they're starting on those things already. And that's likely what they're going to put right back in place, what was there before.
And as they put those new structures into place, I think I also read that the foam glass aggregate can actually get removed and reused again.
Yeah, that's recyclable. That's doubly recyclable from that point of view. That can be used again, and it's likely elsewhere along this entire I-95 corridor there will be a need for it. And so again, it's a very smart. It's economical. There's an efficiency about what everyone is doing. That really plays well into the partnership of the contractors and engineers, and that really are making this all work in a comprehensive way.
And I think what really fascinates me about this whole approach, it's the speed of it, the collaboration that's involved, but also I think it really helps us appreciate how thinking about infrastructure and sustainability go hand in hand, and that's something that is just going to become more and more important in the future. So as we kind of wrap up, our understanding of this particular project, I'd love to have you talk a little bit about how what we're seeing here, might be different if this disaster had happened, 20 years ago versus what might we be thinking about 20 years from now?
Well, yeah, well, certainly years ago, right? We wouldn't the speed at which we'd be able to respond to this wouldn't have occurred in that way. And likely this material years ago would not have been available in this way either. Now, granted, it would be offset by years and years ago, there was less traffic, right? So
Sure.
from that point of view that, there's less traffic to deal with. But I think we're in a much better place with construction methods and all the things that were lending itself to having a quick solution here. Now in the future, we're going to see a lot more of these kinds of materials being used. So not only recycled glass, but a lot of porcelain materials, which is silicon based as well. But so your recycled your toilets and toilet lids and things like that, all of that material is now also being used in ways to recycle them and use them from a sustainability point of view. What we're also combining with this, though, is smart roadways. Years ago, we wouldn't have the electronic messaging on a roadway to tell you, okay, we'll get off at the airport because there's an incident. We don't have ways on our phones like we do now. So there's these ways to help the public themselves, even social media and the way we're feeding that all helps. Like it's certainly a multifaceted solution to it. But we're also looking at things like um, the the rebound of urban sprawl, where we're going to might be in a society where there's less traffic on the roads to begin with, and that other than the goods and services and the 8% trucks traffic I was talking about, you're going to see increased commuter traffic in terms of light rail, SEPTA's regional rail. They even in this case had more bus services. You'll even see a collapse of people who were moving to the suburbs a lot are finding their way back into a
Yeah.
city. So, and things such as we even see it within our city ourselves, right? Some of our streets, like Walnut Street, Chestnut Street, even Ben Franklin Parkway itself, have bicycle lanes on it now and multi-use lanes that people are using in a different way to get about and get through their neighborhoods and their community in a different way that will take some of that traffic off and really plays into, right, a quality of life and a quality of living that's more lived in our communities and less lived on our highways.
No, it's such a fascinating example of how, tackling this one problem gives us a window into all of the systems and all of the decisions that we make as a society.
Sure.
Uh, Mike, we've got a question from a teacher that maybe you can give us some insight into, is to whether teachers could get samples of this foam glass aggregate to show their students.
I don't want to certainly speak for Aero Aggregates, but I'm certain they would be willing to provide that. Like I said, they're a local firm here. It's readily available. There's tons of it. If you even go on the Aero Aggregates website, you'll see some of their yards, and they have. It's something I'd be happy to look into. We do have some contacts there, and we've worked with them before, so I'd be more than happy to look into that and then broker that through the Franklin Institute.
That'd be amazing. So stay tuned. We'll,
Yeah.
we'll let you know if there's a channel to get some of this, real life engineering into your classrooms.
Would it be okay if I said something else about that product?
Sure.
So we're seeing it in one of its applications, but you asked a little bit about the future. Well, it certainly can be applied on different scales and even residential or commercial scales. So I mentioned briefly that this is it doesn't absorb water, this version, but there are options or versions that might be more water absorbent. And then that could be that same similar science-based technology of this aggregate could be used for rooftop gardens. It could be used to make floating docks. It could be used on top of pavilions. So it has like an aesthetic quality to it that you might use in a city on top of plazas. And you can even color it. So maybe you want it green for a rooftop garden or something that's on top of a high rise or even on your residential apartment building. So there are other applications of the same technology that would be appropriate for even on a commercial or even residential use.
As you're talking, Mike, I'm just making so many connections to other fields of science that this is reminding me of, right? I'm thinking about geology and the way that different rocks are formed and the different properties that different
Sure.
types of rocks have. And we've also worked with a lot of material scientists who think about how just different processes of using the same materials can lead to different properties in the final materials.
Absolutely.
So is that something that's happening here? Is that, you described the kind of the pancake and fracturing process to make this. Is there a different process that results in some of these different properties that you're mentioning?
Well, I can't speak specifically to it in terms of the exact nature of that
Sure.
science, or that, the additives that they would use, the type of foam that would be injected, the
Yeah.
temperatures at which it is placed onto the molding structure and then come out. But the additives would do things like that. The additives would make the continuous pores so that it does become more water absorbent. Certainly the color is just the dyeing mechanisms, but it's really the tweak on the core technology of the putting the foam into the silica itself.
And that's such a great example of, the scientific and engineering methodology at work is, how do you tweak the process to experiment with getting different properties?
Absolutely.
And then what kind of uses can you imagine with those?
It's limitless, right? You could, like I said, there's probably a lot of marine applications for this as well. So I could see them in water park areas. I could see them. Well, we see a derivative of this too, as it relates to not glass but rubber. We see those in playgrounds, and instead of the wood chips on the ground for underneath safety measures underneath you know, swing sets and seesaws and things of that nature, you can see the rubberized material. So it's the same concept, just using rubber instead of the crushed bottles.
And are there any environmental hazards with the production of it?
Not to my knowledge. It's non-corrosive. It doesn't leach, which means when you would have liquids or solvents or anything in the soil that might drain through it, that would cause a byproduct of precipitate that sometimes you might see at a landfill. This does not have any of those properties.
That's really cool.
Yeah.
And what do we know about the environmental impact at the site of the collapse? Whenever there's an explosion of fuel, I think there's some concern about the environmental impact there.
Yeah, fortunately, in terms of any of that fuel or petroleum leaking into water sources or nearby creek or even to the Delaware River itself, that we did not encounter that. Now, and there was initial reports about small areas of small sheen that they might have seen in waterways, but nothing of concern. Of course, there was the obvious smoke and particulate
Right.
air pollution that you saw, but that sort of dissipated when the fire was dissipated, and the way they were able to get the fire out so quickly, other than that initial smoke and plumes like that, there was no longer term effects that, at least that I'm aware of, or have been reported.
Well, Mike, thank you so much for joining us today. I think, for all of us who have been watching that live stream and now some of the time-lapse videos of the last couple of weeks, your insights really helped us understand what we were seeing and what we might expect for the future, not just for this particular construction site, but also some of the larger thought processes that you and other infrastructure engineers are really thinking about for the future.
It was my pleasure.
Thank you so much. Thanks to everybody who joined us online. We hope that you'll come explore your curiosity about engineering here at the Franklin Institute. Now that 95 is open, it's easier to get here. But whether it's Amazing Machine or some of our other exhibits, there's always a place to explore your own engineering mindset here at the Franklin Institute. Thanks again for joining us.
Have a good day. Thank you.